So let's go through a sample of problems from 9.4. And the reason we skip over to 9.4 is there's a close connection between linear inequalities with two variables and linear equations in two variables. If we just change one thing, then that would be a linear equation instead of a linear inequality. So to determine whether or not this point or these points are solutions, we just have to substitute them in and see if they're true statements. That's what a solution is. It's something such that when you plug it into the inequality, the equation, or whatever, it gives us a true statement. So in place of x, we'll put the x coordinate. In place of y, we'll put the y, and we'll see if that's greater than 4. So minus a negative will make this a positive, and 4 is not bigger than 4. So this is actually not a true statement, so that one is not a solution. If it had a line underneath it, such that it says greater than or equal to 4, this would be a solution because 4 is equal to 4. But in this one, since there's no line, we don't include where it's equal, just strictly what's greater. And in this case, 4 is not bigger than 4. Now let's try the next one. If we try the 9 and the 4, we would put a 9 for x, 4 for y. 9 minus 4 is 5, and that is a true statement. So that means that ordered pair is a solution to that inequality. Now, after we just look to see what a solution is, then we need to see about graphing inequalities. So to graph an inequality, we need to begin by graphing the equivalent or the corresponding equation. So if we change this to an equation, we need to graph this. Now we could do this a couple of ways. We could come up with two ordered pairs that are solutions. We could pick an x, get a y, pick a y, get an x. We could find the intercepts, or we could solve it for y and use the slope in the intercept. Either way is fine. I'm going to do the x and y intercepts. So I'm going to put a 0 for x and see what the y-intercept would be. So if we let x be 0, 0 plus y is y. So when x is 0, that corresponds to y being 5. Now if we let y be 0, we can find the x-intercept. So this time, instead of plugging in for x, we plug a 0 for y. X plus 0 is x. So that makes the x-intercept also 5. So let's put in a grid and let's plot those. We have a y-intercept of 5, an x-intercept of 5, and we need to draw a line through there. Now before we draw our line, we have two choices. We have either a solid line or a dotted line. When we are supposed to include where we are equal, then that means we need to include the line that we determine here. So to include it, that's going to be a solid line. So we would just draw a solid line through those 2 points. And that's where x plus y equals 5. Now we just need to determine on which side of that line is x plus y less than 5. So we can do this by doing a test point. We can pick a point on either side. For example, if we pick this test point, that's the point over 1 up 3. If we put a 1 for x, a 3 for y, is that going to be less than 5? And when we simplify, yes, it is. So that means that points on this side of the boundary are indeed solutions to this inequality. That would work no matter which point we picked on this side of the inequality. If we consider this point 2, 1, 2 plus 1 is 3, that's less than 5. If we think about the origin, that's 0, 0. 0 plus 0 is 0. That's less than 5. So every highlighted point on the bottom side of this line would be a solution. Now, just for illustration, if we pick a point on the other side of the line, any point on the other side of the line, if we substitute that into our inequality, that's not a true statement. Hence, there are no solutions on this side of the line. So all of these points and the line itself are the solutions. Let's look at this one. Our boundary is going to be x plus 3y equals negative 3. And for practice, let's solve this for y this time so that we can use our slope and y-intercept. And in fact, I'm going to go ahead and solve it for y before we change it to an equation. So if we want to solve it for y, then we want to get this term on one side, everything that doesn't have a y to the other side. So what doesn't have a y? This over here, this. So when we have things that are added or subtracted, then we have to either add or subtract to make things go away. These are terms. So to make a positive x go away, we would subtract x on both sides. So x minus x cancels, leaving us 3y is less than or equal to, if we're trying to get it in this form, let's put the x term first and then the constant. All right, now that we have the y term by itself, we need to get rid of the coefficient. So we divide both sides by 3. So we get y is less than or equal to, and it turns out if we have two terms, we divide each of those by 3. We divide the x term by 3 and the constant by 3. So we get y is less than or equal to, negative over positive is negative. The coefficient of x on top is 1, so we can call this 1/3 x. 3 over 3 makes 1. So this is just another way of writing the same inequality we had at the beginning. So that's good practice for isolating our variable. Do we have to do it that way? No, not exactly. We could leave it in this format, and we could pick a y, get an x, or pick an x, get a y. But again, we're going to do slope-intercept for practice. So if now that we have it solved for y, -1 tells us where our y-intercept is. So we have a y-intercept of -1, and we have a slope of -1/3. So if we're doing rise over run, we need to put the negative either on top or bottom. So it doesn't matter which, as long as we put it one or the other. So if we put it on top, then we would rise a -1, which would mean go down 1, and then run 1, 2, 3 in the positive. Down 1, 1, 2, 3 in the positive. If we were to have put the negative on bottom, then we would have gone up 1 and then left 3. 1, 2, 3. Up 1, left 3. And when we do that, we'll notice that all of those points are in line with each other. Notice we include where we are equal because of the line. The line here is where we are equal, so that's solid. So now we just have to decide which side do we need to highlight. One benefit to solving our inequality for y is that if we have y by itself, less than means to highlight below it. Greater than would mean to highlight above it. So I suspect that we're supposed to highlight below it. Now, I'm going to check that just to be safe. And we can even go back to the original to check to even be safer. Oops. So the original is x plus 3y is less than or equal to negative 3. So if we test a point below the line, we could test this point, 1, negative 2, and that should be a solution. If we put a 1 for x and a negative 2 for y, that should be less than negative 3. So we get 1 positive times negative is negative 6. 1 minus 6 is negative 5. And that is true. Negative 5 is farther to the left than negative 3, so that's a true statement. As we suspected, that is a solution. Now, if we check a point like the origin, if we put a 0 in for x and a 0 in for y, we would get 0 plus 0, which is 0, and 0 is not less than negative 3. Hence, that point's not a solution. So as we suspected, we were supposed to highlight below the line, not above the line. By drawing the equation of the line, by changing it to an equation, y equals negative 1/3 x minus 1, and graphing that line, we got our boundary, and then we test a point on each side of the boundary to determine which side we should highlight. Let's do this one. This one would be fairly easy to get y by itself. Just subtract 2x on both sides. If we subtract 2x on both sides, then 2x minus 2x is 0. So that leaves us y on the left, minus 2x, and positive 5 on the right. Remember, if we want to get a term by itself, we either add or subtract. If this is a positive 2x, we need to subtract 2x so that those cancel. All right, so our boundary is going to be y equals negative 2x plus 5. So our y-intercept is at 5. Our slope is negative 2, or as a fraction, negative 2 over 1. So let's graph that. Here's our y-intercept. And if our slope is negative 2 over 1, we go down 2 over 1, down 2 over 1, down 2 over 1. And then we can just draw a line through those points. And there's our boundary. But I did something wrong there, and I did it on purpose just to see if you're paying attention and to illustrate a point. Something is different about this problem, compared to the other ones. Don't cover that up. Notice our inequality does not include where is equal to. It's just less than, not less than or equal to. So if we don't include where we're equal to, we are not supposed to have a solid line. We're supposed to have a dotted line. A dotted line lets us see the boundary without actually including points on it. So now we just need to determine which side of the boundary works. So I'm going to pick the origin as a test point. And if we take our original inequality, I always like to go back to the original just in case I made a mistake along the way. Plug a 0 for x and a 0 for y and see if that works. Well, 0 plus 0 is 0, and 0 is less than 5. So yes, that point is a solution. So we need to highlight this side of the line. Everything over here gets highlighted. Now, if we pick a point over here, let's say 3, 3, to test it, we substitute 3 for x and 3 for y in our original. 2 times 3 is 6 plus 3. 6 plus 3 is 9, which is not less than 5. So that point doesn't work. So that means we do not shade this side of the line. Now you might say, why did you pick those points? I just randomly chose points. I chose the origin because that is an easy point to plug in. It's easy to put a 0 for a number and do the arithmetic. 0 times something, 0 plus something, that's easy. And then I just randomly picked an ordered pair that's on the other side of the line to test it. But you can pick any point that's not on the boundary. Okay, this one has a boundary of y equals 4. Y equals 4. So we have to remind ourselves, what kind of line is y equals 4? This says that the y value is always the same. Remember, y is up and down, so we're always up the same amount. So if we start at the origin, we could go up 4. If we're over 3, we're up 4. If we're over 7, we're up 4. If we're to the left, we're up 4. So that makes a horizontal line. Even though the y direction is up and down, if the y direction is constant, that means every point is at the same height, at the same y value. We make it a solid line because equal to is part of our solution, not just less than, but also equal to. So let's come in, put a solid line. Right there. And then we have to see which side is y less than 4. We know where it's equal to 4. It's equal to 4 right here. But where are the y values less than 4? Well, you might be able to determine that without even plotting a point. If we pick a point down here, these y values are 3, 2, 1. All of these y values are less than 4. So we shade down here. But if we were to look above here, these y values are bigger than 4. So these wouldn't work.